Okay, as promised, we're looking at a short video, hopefully a short video here, which is going to get us through the definition of the derivative. I'm going to share my screen so you can get a sense of, a picture of this stuff as I'm talking about it. And hopefully if you hang in here, you have a good understanding of this, and this will take you as far as you want to go. And there might be several times when we're going to come back to this definition countless times between now and the end of this course. Comes up on the AP exam all the time anyway. So I've got a little picture here, definition of the derivative, and essentially what it is, the derivative, that is, it's a function that's going to provide a formula to determine the slope of this function that we're taking the derivative of at any x value. So again, it's a function that kind of predicts the slope of its, like, I want to say maybe its mother function, if you will. Okay, so what I've done is I draw kind of an arbitrary curve here of f of x. Could be anything, doesn't have to be above the x-axis, doesn't have to have a positive slope or anything like that, just a random picture. And I've highlighted this point here. And because we're just talking in the abstract, we're talking about a random point, so I just call its coordinates x comma f of x. Now, from your knowledge of like what I refer to as like 7th grade slope, the only way to find the slope is to have 2 points. So what I did is I took my x value down here. Let's get a pointer here going. And I took this x value down here and I said, okay, let's move away from x, and we're going to move over to the right. We could move to the left, it really doesn't matter. But I'm going to move h units over. So that puts me at this new point here, and that new point on the curve, I'm just going to put it up there. So it has coordinates, and we have to think about what its x coordinate is. If you start at x and then you move h units to the right, like if you started at 3 and then you moved 4 units to the right, you'd be at 7, right? So that's 3 plus 4 is 7. So because we're starting at x and we're moving h units to the right, the coordinates of this guy over here are going to be, or at least the x value is going to be x plus h. So we say, okay, the x coordinate is x plus h. And the y value, we have no idea what the function is, so we're just going to call it f of x plus h, or the y value of that function when the x value is this new number x plus h. And while we're looking for this slope, or the slope of the curve right here at this x value right there, so if we were to say that's kind of what we're out to capture, is what's the slope of that little green dotted line. What we could do now, because we have 2 points, is get the slope of this red line, referred to as a secant line. And that would be a piece of cake. Finding the slope of that red line would simply be, and we might refer to that as like the average, what we talked about in class, the average rate of change between 2 points. It's just y2, which is f of x plus h, the y value at the second point, minus y1, which is this y coordinate at the first point, so that's just f of x, over x2, which is x plus h, so x plus h, minus x1, which of course is just x. And you look at that and you go, okay, well, we can clean that up just a little bit. Look at the denominator, because it's x plus h minus x. So that whole thing is just going to simplify, at least in the denominator, to simply h, because you have a positive x and a negative x, and of course they cancel each other out. Now look at that denominator. It represents, this fraction, this difference quotient. A difference quotient is, it's a quotient, numerator, denominator, that has differences in it. Difference of the y's over the difference of the x. Hence the name difference quotient. Has h as its denominator. Remember, that represents the change in x. Well, look at our picture right here. H is how far we moved from x over to x plus h. So it makes perfect sense that h is the change in the x values. So with that in mind, we say, okay, that's, if we wanted the slope of this red dotted line, we're done. There's a formula for the slope of the red dotted line. The problem is we don't want the formula for the slope of the red dotted line. We want a formula for the slope of this green dotted line. And so what we're curious about is, that's great when my approximation, this red dotted line, is a horrible indicator of the slope of that green line. What I should really be doing is taking this point, instead of having it, that secant line right there, what if I took this point here and said, instead of drawing it there, what if I drew it like super, 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 super close? The phrase I was using in class is infinitesimally close to that first point. And so, of course, what we've done here is we've taken this change in the x values, this h value, and we've just, you know, completely, completely like shrunken it down. So rather than looking like that, it's going to look like some kind of miniature version of that. I'm just going to kind of really shrink that up so that you could imagine that thing. I can't make it go that small. But you get the idea now that we've taken the h value, that the change in x, and made it really, really small. So maybe to accurately indicate that in my picture, maybe I could, you know, take my point here, put it like there. And that's, I mean, you can see it right there, that secant line is a much, much, much better approximation than the original one that was, you know, way off. So imagine that h value down here getting smaller and smaller and smaller, so that it was, these 2 points were virtually right next to each other. And we can say, you know, what we can do is look and see what's going to happen to this difference quotient, what's going to happen to this thing when h gets really small. And of course, what you would do there is you'd say, all right, well, let's take a look at that. And we'll say for the green tangent line, instead of looking at an average slope, we'd be looking at an instantaneous slope. And we would just be saying, what's going to happen to that f of x plus h minus f of x over h? And again, that's simply difference of the y's over difference of the x's. But what we want to do is find out what's going to happen when h heads towards 0. Basically, when this distance right here is virtually 0. And again, just like every other limit we've done when we did those numeric examples, and you got numbers, you know, if we had a limit as x was going to 0, we'd see what happened when we get x closer and closer and closer to 0. And eventually you'd see the y values, you know, becoming, you know, something like 0.49, then it was 0.499, that was 0.4999, that was 0.499999. And it was really clear that what was happening was it was getting close to 1/2. Well, this right here is our formula for the slope at x. And it seems kind of, you're like, well, that doesn't seem very helpful. First of all, your first instinct might be, you know, our first rule of evaluating limits is plug this guy in and see what you get. Well, in this case, if you plug 0 in there, you'd have f of x plus 0 minus f of x over 0. And of course, x plus 0 here, right there, that would just become an x. And of course, we had f of x minus f of x, that's going to be 0. Oh, there's our good friend 0 over 0 again for the 9 millionth time since we started the course. And you say, okay, well, something's going to happen. We're going to have to use one of our algebraic manipulations or something like that, factor and cancel, or maybe simplify a complex fraction with a common denominator, multiply by the conjugate. There's all sorts of algebraic things we can do to figure out what the limit is when we get one of these 0 over 0s. But the moral of the story is what we have now is a definition for the instantaneous slope of a function at, you know, any x, and it's given by this limit expression of f of x plus h minus f of x all over h. Now, you might be thinking, like, what does that look like in practice? How the heck am I going to find this thing? Because that's really what we're after. Well, that's the next class. But I needed you to kind of see, to take the mystery out of this expression so it doesn't look quite so daunting as really just y2 minus y1 over x2 minus x1 when the x and the two x values are really, really, really close together. And so we can expand this notation to say that if we're talking about some function f of x, which is really where this whole thing started, if we're looking for a formula that provides a formula to determine the slope at any x value, we define that using the notation f prime of x, and that prime up there, that little, you know, apostrophe, indicates that this function, this new function that we're going to get, is related to the original function f of x. It's like, we don't want to just choose some new letter like g of x or r of x, because we want to tell the reader that this function is telling us about, like f prime is telling us about f of x. There are other notations we can use. I've referenced a couple in class today, but that's going to be good. The one we saw in class today where I had the first example, we had f of x was, I believe, x squared plus 3x plus 2. And yeah, that was it. And then we did f prime of x, and we found out that that was 2x plus 3. So if I'm looking at this as a mathematician and I see that notation, f prime of x is 2x plus 3, that's telling me, hey, there must have been some function f, and that we were curious about its slope or its rate of change, and this function f prime is what predicts that for us. All right, so that's going to get you ready for class next time, where we're going to do several examples of this. But that is our primary definition of the derivative. You're going to hear me refer to the definition of the derivative countless times. So hopefully that does it for you. So that's all for now. I will see you in class. Peace out.